So I actually want to start with a question today for you all. How many of you are dealing with challenges in your day-to-day work? Some kind of complexity, some kind of problem that you are solving? Yeah, most hands. Software development is inherently a complex thing, right? But I want you to actually just think for a second, where exactly are them problems coming from? Is it coming from the fact that you're just solving a really hard problem? There's some really complicated algorithm you need to implement, you're dealing with 1 billion users, something like that. Or is it the fact that you're working with a .NET Framework 1 application deployed on a Windows server underneath someone's desk somewhere in the office? That brings about its own set of problems, right? Or have you chosen to deploy your application on Kubernetes and you spend every single waking minute of every single day wondering when that next cluster upgrade is going to come around and break your system? All these things bring about their own complexity. And at its core, this is a talk about dealing with complexity. And by the end of this talk, I want to leave you with the ability to be able to take your application code, solve the problem that your users actually want you to solve, and worry only about that bit and not worry about all that other unnecessary complexity. I'm James Eastham. I'm a serverless advocate at Datadog. Before that, I worked at AWS for 3 years. I'm a Microsoft MVP. I'm an AWS community builder. And if any of you have seen any of my talks before, you've seen any of my content online, you'll know that there's one thing I love talking about almost as much as serverless and event-driven architectures, and that is pizza. Who else thinks pizza is the greatest food on the planet? Okay, those of you with your hands down, come on, people, really? Really? So for the purpose of this talk, for the rest of this talk, for the next hour, I want you all to completely forget your day jobs, forget your Jira backlog, forget your on-call, forget everything, because you're all now developers for a completely fictional pizza delivery company called Plant-Based Pizza. And your application today, you're a reasonably early stage startup, you've built a monolithic application, you've deployed that in the cloud, and that has worked reasonably well up until this point. But you're starting to hit some problems. Your developers are starting to get frustrated. You're starting to get in each other's way. You've got this big monolithic code base. You're all trying to conflict. You're all making conflicts on the same pieces of the code. You've got clashes. You can't ship features fast enough. No, everybody's getting frustrated. Nobody more so than Helen. Helen's your CTO. And one day you're sat at your desk and a Slack message pops up and it's Helen. You think, this is kind of odd. CTO's messaging me directly on Slack and she wants to have a meeting in 15 minutes. Okay, that's not sounding good. Maybe this is the end. Or maybe people are starting to notice all the good work I'm doing. So you jump on a call with Helen. Helen, you're not losing your job, don't worry. She says that you've got a task. You're going to be in charge of breaking out the first microservice from this monolithic application. But she gives you some constraints to work with. The first constraint is that you're going to be the only developer working on the project. You can't rely on anybody else internally, no infrastructure teams, no support teams, no other developers. It is all on you to break out this first microservice. And actually that promotion you've been waiting for a couple of years now, yeah, that's going to rely on the success of this project. So pretty stressful, also pretty fun, right? Because you've got a lot of freedom now to choose to build this first microservice however you want. So you go off and you start having a look around the code base and you think the menu service, the part of the code base that displays all of the available pizzas, that's the bit that you're going to break out. You choose that service because it's not a tier 0 absolutely critical service that if it goes offline everything breaks, but equally it's not something so completely irrelevant that nobody actually cares about it. And that's normally a pretty good heuristic if you're doing any kind of migration or modernization project. Picking something in the middle is normally a pretty good place to start because it'll prove out the element of criticality without risking taking absolutely everything offline. So as you start to look at breaking out this bit of the code base, you realize that you're starting to hit a problem of complexity. And there's primarily 2 different types of complexity that you'll deal with. There's essential complexity and there's accidental complexity. Now, essential complexity, that's the complexity that you cannot get rid of. In this menu module that you need to break out, the complexity there is that you need to reliably display all of the available pizzas to all of the users when they come to look at them, right? There's inherent complexity in that problem. And all of the things that all of you are actually building will have their own inherent complexity that you can't actually get rid of. Accidental complexity, though, that's complexity that you have control over. That's the complexity that comes from how you choose to build and run your system. I'd argue that a monolithic system running in a single container, connecting to a single database, has lower technical complexity than a distributed set of hundreds and hundreds of microservices, right? Because there you've got complexity in your service communications, complexity in your reliability, complexity in your observability. You've got all these other things that you introduce. Now, microservices isn't necessarily a solution to technical complexity. It's a solution to social complexity. What you're hitting up against in your monolith is social complexity, because you've got all these people who are all contributing to the code base, all trying to change things that are getting in each other's way. So microservices is a solution to a social technical problem. The issue you get when you start to break out microservices is that although you start to lower some of that social complexity, you've got a smaller group of people all contributing together working on a single thing, and the complexity of an individual service is lower, the complexity of the system as a whole increases a lot. Starts to look a little bit something like this. So you decide that actually you want to start reducing this accidental complexity. You want to break out this first microservice. Remember, you're the only person working on this project, so you want to do that with as low complexity as possible. How exactly do you go about reducing complexity? And this is where I think serverless becomes really powerful. Now, serverless is a word that's kind of been co-opted by so many marketing teams now, and so many services have been told that they're serverless and they're not really serverless. What does actually serverless mean anymore? So I want to try and redefine that for you. In my view, serverless is about reducing accidental complexity. It's not about does it scale to zero, does it scale up, does it scale down, do you pay per use? It's about reducing complexity, reducing that need to manage the underlying infrastructure. So a quick question for you all, actually. When was the first serverless service ever announced, right? And if you think it's been announced in the last year, just chuck your hand up. Okay, not in the last year, of course, that's kind of obvious. The last 5 years was the first ever serverless service announced. I can see some of you trying to do the maths in your head when that certain service came out. What about the last 10 years? Was the first serverless service announced in the last 10 years? Couple of hands, okay, yeah. Last 15 years? Okay, good. What about the last 20 years? Interesting, okay. Those of you who went in the 15 to 20 year range, give yourself a medal, give yourself a pat on the back. Because actually, the first ever cloud services ever announced, not the first serverless services, the first ever cloud services ever announced, Amazon SQS and Amazon S3, they went GA back in 2006. Actually, SQS went in beta in 2004, so that would be just about in the 20-year range. The cloud is inherently serverless. I always find it kind of interesting when you see the Cloud Native Computing Foundation and it's all about running Kubernetes on servers, and I'm like, I'm not really sure, is that really cloud native? So the cloud was born serverless. If you're running things in the cloud, you're using managed services, you are using serverless technologies. Serverless is a spectrum though. Serverless is not a binary decision. You don't choose to be serverless or not be serverless. You can choose to run your application in more or less of a serverless way. This spectrum looks a little bit like this. At one end of the spectrum, being as serverless as you physically can, it is all about reducing your operational overhead, reducing that accidental complexity, reducing that need to manage infrastructure, to run servers, to manage databases. The trade-off you get there, though, is that you lose flexibility. A lot of these serverless services are very, very opinionated. They don't really give you a lot of control of that underlying infrastructure. So that's the trade-off you make. At the other end of the spectrum, of course, you've got more flexibility. You get flexibility, you take on more overhead. This isn't the only dimension to consider, though. There's a cost dimension to all of this. And if you could find a way to directly compare a serverless function to a comparable virtual machine, which is actually a really, really hard comparison to do, the bill you get from your cloud provider is almost always going to be more expensive for a serverless service than not. Which kind of makes sense, right? Because you're paying Azure, you're paying AWS to run that infrastructure for you. What that doesn't take into account, though, is the human cost. Because if you choose to take on more overhead, you choose to need to manage infrastructure, well, you need to pay people to manage that infrastructure, right? That's why platform engineering is such a big thing at the minute, because you need people to build a platform. Now, for me personally, I'd rather pay AWS to be my platform team. Thank you very much. So what does this actually look like from a practical perspective when you actually come to breaking out this menu service now? So on the far left of this spectrum, you've got services like Lambda, like Azure Functions, Cloudflare Workers, Google Cloud Run, the services that many of you probably thought of when you heard the word serverless, right? The kind of typical serverless function. They scale up when there's work to do, they scale down again when there's no work to do, and you only pay per use. You only pay when your code is running. But as you start to take a walk down this spectrum, you start to come to services like Azure Container Apps, Amazon ECS, AWS Fargate, services where you can build a container, give them a container, say, I want this much CPU, this much memory, thank you very much, run that container for me. And then as you walk a little bit further, you start to get into your Kubernetes services where the cloud provider is going to run the control plane of Kubernetes, but you need to run everything else yourself. You need to install things on the cluster, manage the underlying infrastructure. And then, of course, you've got your actual virtual machines running things on the actual virtual machine. Then right off over in room 5 somewhere, you've got that Windows server sat underneath someone's desk in the office. So this is the spectrum of options you've got from a compute perspective. But it actually isn't all about compute. Your menu service is going to need a database. Imagine, for the purposes of this, it's a Postgres database that you need. So you could choose to run Postgres on a virtual machine. That's one option you have for running Postgres. People, it's 2025. Let's not be running servers anymore. You could equally completely refactor the entire code base and use a proprietary database service, something like Dynamo, Cosmos DB, Google Firestore. You could use a managed database service that all the cloud providers have some kind of variation of, or you could adopt a third-party SaaS product that are popping up, companies like Cockroach, like Neon. If you haven't heard of Neon, by the way, and you're running Postgres, truly serverless Postgres databases scale to zero, they scale up, they allow you to branch your databases. I'm not affiliated in any way, it's just a really, really fantastic service if you're using Postgres in production. Now, of course, there's no right or wrong place to be on this spectrum. Sometimes you might need more control of that underlying infrastructure. You might need a specific GPU, maybe you're training an LLM. Okay, going as far left on that spectrum maybe will be necessary. We used to have a heuristic when I worked at AWS, and it was if your ability to dynamically scale a specific type of infrastructure, Kubernetes is really good, it's differentiating for your business, then Kubernetes is a really good thing because it's really good at dynamically scaling things up and down really specific types of infrastructure. But generally, for most workloads, you're going to want to think serverless first. Thinking serverless first is simply sitting as far left on that spectrum as you physically can, reducing your operational overhead as much as physically possible. So with your menu service, whereabouts on this spectrum should you choose to sit? You need to build an API that exposes menu items to your users, and you think, well, let's be serverless maximalists, let's go as serverless as we physically can, let's build this with functions. So just a quick show of hands, who's building with Azure today, running applications on Azure? And AWS and other clouds. I'm going to have to apologize for other clouds. Sorry. So for the rest of the talk, I'm going to flip between Azure and AWS. Other clouds, come and talk to me afterwards because I'd be interested to see what you're using. So you choose to start building out the typical kind of serverless API. You've got some kind of API endpoint in AWS, that'd be API gateway. Azure Functions, your function app has an endpoint. And then you've got individual functions handling the individual routes on your API, some kind of persistence underneath. And regardless if you're using Azure Functions or Lambda, the definition of a function looks broadly the same. You've got a class, that class has got methods, and you tell the service which method to invoke when that function gets invoked. In Azure, that's using the Azure Functions SDK, you add attributes to your methods. In Lambda, you are telling Lambda, invoke this method in this class in this namespace. Ever so slightly differently, fundamentally the same idea. You define a method in your code base, you tell the service, run this method when the function is invoked. So you go off and you build all your functions, you think this is fantastic, we're building with serverless functions, we're serverless first, we ship our code, we ship the first version of the menu service, fantastic. Everyone's happy, promotion in the bag, we can all go home. Then Helen comes back, and believe me, she's not as happy as she looks in this photo. I just couldn't find a photo where she looked any angrier, so just imagine she's really angry. She's angry because your users are now starting to get frustrated. Your users are getting frustrated because intermittently, they're starting to see really slow response times in your API, in the front end. Sometimes your staff are trying to create new recipes, new menu items, and it's just not working at all. Or a user's trying to place a really big order, and it just errors, it just doesn't work. Kind of annoying. We thought this serverless thing was great. Thankfully, because you're all fantastic developers, you added telemetry to your application. You added some observability. So you go off into your observability backend and you look at all of the trace information for your endpoint for listing all of the available menu items. And you look at the response times and you're like, this is pretty okay. You've got double-digit milliseconds, some just about getting into the triple-digit milliseconds, but for the most part, it's double-digit millisecond response times, which is great, right? Users should be happy with that. So you decide to sort this list of responses by duration. Okay, not quite as pleasant a picture. You've got a lot of response times here that are in the half a second range, which still isn't horrendous, but equally, if you're used to double-digit millisecond response times, half a second can feel like forever. So you go and zoom in and have a look at one of these traces. You actually have a look at the internals of the request. So that very top bar you can see there is the actual end-to-end of Amazon API Gateway, the actual total API response time, which actually is a second. Then the actual invoke time of the function was half a second. So that was the 523 milliseconds you can see there. So actually your API response time was in total a second, which isn't ideal in some front ends. And you'll notice for your actual invoke there, you've got two spans for the actual invoke of your function. You've got one span that took 500 milliseconds, one span that took 90 milliseconds. So there's something happening inside your function that is taking an abnormally large amount of time. So you go and zoom in and you have a look at that. The AWS Lambda cold start. I'm seeing some nods already. That's good. Who's here experienced cold starts? Who here hates them with a passion? Yeah, most hands. Some handshake. I like that. Cool. So this is a fundamental feature of how these services work. If you compare this to your typical application, you're going to build an ASP.NET Web API. You're going to containerize it. You're going to run it. That environment is going to be running, and it's going to handle multiple requests concurrently. If 10 requests come into your API, they're all going to be handled by that same running instance. Lambda, each running instance of your application can only handle one request at any one time. It's a concurrency of one inside an individual environment. What that means is that internally inside Lambda, your application looks a little bit like this. You've got lots and lots of running instances of your application, all handling one request concurrently, which makes your application kind of this makeup of all these running instances of your application. What actually happens under the hood is what's known as the execution lifecycle. So one of these environments is created. These environments are completely isolated micro VMs. It's got its own dedicated CPU, its own dedicated memory allocation. That's going to be created first. Then your code is going to be downloaded. You can deploy code as a zip file or a container image. That code's going to be started up. That period of time there is what's known as the initialization phase, or the cold start. And then your request is actually invoked. What this actually looks like in practice under the hood is a first request comes into your Lambda function, that initialization phase is going to happen, your code's going to be invoked. If a second request comes in whilst that first request is still in process, another environment is going to be created, that's going to be handled separately. Then if a third request comes in, whilst that second request is still in process but the first one is finished, that environment is then reused. So there is an element of environment reuse here. This is what will be known as a warm start. Feels horribly inefficient, doesn't it, to do that? So how does this work in Azure Functions? It's ever so slightly different in Azure Functions. There are some similarities. So in Azure Functions, you define a function app. A function app is where you put your configuration, your app settings, your security, and your function app will be linked to an app service plan of some kind. And it's the app service plan that will determine the capabilities of your function, what kind of resources your function has. And then inside your function app, you've got your individual functions. And it's the app service plan that you link to that will determine how a lot of this works. Now, late last year, maybe early this year, I can't remember exactly when it went GA, Azure announced the Flex consumption plan for Azure Functions. This should probably be the default for most workloads you are building going forward, because Flex consumption gives more Lambda-like behavior in a sense of each individual function will scale completely independently. It scales up on its own, scales down on its own. Plus, you also get VNet connectivity, which used to be limited to, I think, premium, maybe standard as well. I'm not 100% sure on that one. So Flex consumption gives you that Lambda-like behavior. Each independent function can scale up and down independently. Another benefit of Azure Functions is that they can handle multi-concurrency inside a single running instance. Now, that each individual function scales independently has a really small but. And the but is for HTTP triggers. If you've built an Azure function that's triggered by HTTP calls, all of the functions in a function app that are also triggered by a HTTP call scale together. And I actually think this is a really good feature of Azure Functions. So imagine a GET request comes into your Azure function. I want to list all of the available menu items. Your function's going to scale up, but all of your other functions that are also handling HTTP endpoints are going to scale up together. That means, depending on what you set the concurrency as, that same running instance of your application can now also handle multiple requests. Now, if you were to set the concurrency to 1, which I wouldn't advise you do for a HTTP endpoint, but if you did, that another request comes in, that's going to be handled by another running instance. That's going to need to scale up another instance. Of course, you probably don't want to do that for HTTP endpoints. You're probably going to want all of that handled by that same running instance. So I actually think this is a really nice behavior of Azure Functions with flex consumption, particularly in that if you've got functions linked up to service bus queues or topics, they're all going to scale completely independently based on the load that's coming through the queue or the topic. But your HTTP endpoints all scale together and they can handle multiple concurrency. While I'm talking about this topic of scaling, one other thing I did want to touch on actually is the database that you connect your functions to. Because if you think about a typical application, your application is going to start at once, it's going to create a connection to your database, and you've got one connection to your database or a pool of connection to your databases, all requests are using that same connection, right? Lambda, Azure Functions, where you're scaling up to have lots and lots of running instances of your application automatically, means you're going to get lots and lots and lots of connections to your database, potentially. So this is just something to be aware of if you're connecting Azure Functions, AWS Lambda, to more traditional databases, Postgres, SQL Server, something like that. Just be aware that your function might scale up, and that can really quickly start to overwhelm your database, particularly with Lambda and the way scaling works inside Lambda. So back to this cold start problem. I actually think cold starts get a bit of a bad rap, actually. Partly because whenever you deploy a new version of your function, you change some configuration, you are guaranteed to get a cold start because all the existing environments are going to be blown away. So as a developer, it can feel like you're getting a lot of cold starts because you deploy a new version, you get a cold start, you make a change, you deploy it again, another cold start, every single thing is cold start. So the thing I always recommend if you're starting to work with any functions is to run some load through your service to see how it behaves. Try and predict what your actual user load is going to be and run that through it and see how it actually behaves. The curious thing about functions is that they tend to work better the more load you give it. The other thing I'll say is that when you compare the cold start of a function to the cold start of a container, imagine you're running your application in a container and you need to scale that container up. Well, for that to happen, you're going to have some kind of metric to base that scaling behavior on. You're going to need the metric to go above a threshold, you're going to need an alarm to trigger, you're going to need the scaling to actually happen, your container to actually start up, your container to actually be healthy. The cold start of a container is going to be a lot slower than the cold start of a function. Back when I was at AWS, we used to do a lot of analysis on cold starts, and we ran some analysis across every single invoke of every single Lambda function across every single customer account. And cold starts accounted for less than 1% of the total invokes of all Lambda functions. So the takeaway there is if you're using functions, run some load through the function to see what it is. Now there are a bunch of little hacks that you can do. Both Lambda and Azure Functions support the idea of always on. They call it slightly different things, but you can have a set of these environments running all the time. Great. You can use things like native AOT to try and really optimize the performance. You can write hacky little scripts that hit your function every now and again to try and keep it warm. There's these things you can start to do. But actually I would suggest you're starting to introduce some complexity again here. You're starting to have to do some really weird things to work within the constraints that these services bring upon you. So would it not be more sensible just to be a little bit more pragmatic in this case? To come back to this spectrum of services we've got. And did anybody see this article recently, actually, on the internet, where Microsoft announced that they'd rewritten the TypeScript compiler? Yeah, a few nods. So Microsoft announced that they'd rewritten the TypeScript compiler in Go. The .NET community lost their minds. If you saw anything on the internet, the community was like, .NET is dead, Microsoft don't care about .NET anymore, why have they not used .NET for this? The Rust developers all kind of charged in and said, why did you use Go, why did you not use Rust? If you read the article and watch the video, it was actually a really pragmatic engineering decision. The way the current TypeScript compiler worked was functionally, semantically very similar to how Go works as a language. So rather than completely refactor the entire code base, change how everything works, they made a pragmatic decision. Part of our jobs as developers and architects is being pragmatic, is choosing the right tool for the job. So maybe for this workload, we think, well, we could do a lot of little things to try and get around the cold starts, to get around some of the other constraints that functions bring upon you, or we could just run this on a container. Now, when it comes to running containers, you've got two options, really. You can either choose to use the managed service that the cloud provider gives you, or you can choose to run it on Kubernetes. Now, I think we're probably all in agreement that there's one clearly good choice there. Yeah, it's this one. Anyone didn't know? So you can choose to use the managed service that the cloud provider gives you. On AWS, that is Amazon ECS and AWS Fargate. Amazon ECS is the container orchestrator. This is the thing that's actually going to orchestrate the containers, to start the containers up, to scale them down. Fargate is serverless compute. With Fargate, you can simply say, this much CPU, this much memory, go. You can equally use EC2, a virtual machine, inside Amazon ECS. You can use EC2 to provide the compute for your ECS cluster. Fargate is just another way of doing that. Equally, if you're using EKS, you are using Kubernetes, you can use Fargate inside EKS as well. So ECS is the orchestrator, Fargate is the compute. On Azure, you've got Azure Container Apps. Probably my favorite cloud service at the minute, actually. So with Container Apps is an abstraction on top of Kubernetes. Azure chose to do it slightly differently to AWS. So it's an abstraction on top of Kubernetes where you as a developer don't need to care about Kubernetes. Great, that's a win. With Container Apps, you define a Container App environment, dev, staging, prod, James's test environment. And then inside that Container App environment, you deploy container apps. When you deploy a container app, the bare bones you need to say is, here's my container, I want this much CPU, this much memory, I want public ingress, I want internal ingress, I want no ingress, application runs. All the apps inside a container app environment, if you've got internal ingress enabled, can talk to each other. And Container Apps also integrates with Dapr, the Distributed Application Programming Runtime. It's probably a whole other talk to talk about that. If you're not familiar with Dapr, it's kind of an abstraction that gives you a set of building blocks for common things that you need to do in distributed systems. Secrets management, service discovery, service-to-service communication, pub/sub. It acts as a kind of abstraction. So the Dapr integration with Azure Container Apps is fantastic, really, really good. It allows you to deploy a container app and say, this is the orders service, this is the menu service. And then when another service needs to call the menu service, it just says, make a call to menu, and Dapr manages the rest. It's a really, really cool service. What you're starting to encounter here, though, is one of the only constants, I think, in all of software development, and that is change. Things are constantly changing. We're constantly having to deal with change, right? It's changing business requirements, changing user profiles, changing user loads. Maybe your executives decide that they want to focus on cost optimization or sustainability. Maybe there's a change in government somewhere in the world that affects the economic situation of every country in the whole entire planet, and then suddenly we all need to refactor things. Like, change is inevitable in software development. But you start to look back at your code base, and you think, well, to run this in a container, we need to adopt some kind of web framework, right? We need to adopt ASP.NET, we need to adopt Express or Spring, whatever programming language you're using. You need a web framework. But we've written this whole thing in Azure Functions or a Lambda, and we've kind of used the semantics of Azure Functions or of Lambda. This is going to be a problem, right? And you go and have a look at your code base. You go and have a look at your code for your create function, the endpoint on the API that staff members can call to create a new pizza, to create a new recipe. And you look through the code base a little bit. You decided to refactor to MongoDB as part of the migration for reasons, hand wavy. So you inject your MongoDB connection, your MongoDB, your SDK, and then you've got your Azure Functions specific stuff. You've got your Azure Functions attribute. You've got your HTTP trigger that tells Azure Functions this is going to be triggered by HTTP. Then you're parsing the contents of the body of the HTTP request into an actual business, an object that's relevant to your business. Then you're making calls to your database. You're running some custom business logic, more business logic, another call to your database, another call to your database, and you've made a terrible mistake if you're writing your functions like that. I've written functions like that, by the way. I'm guilty of this as well. This is a problem because you've started to tie everything that your application is concerned with up in a single code file. I think it's kind of the downside of calling these things functions, Lambda functions, Azure Functions, is it can easily make you think, well, I've just got this one function that I just write all my code in and it just runs. Now you've got your Your database concerns, your weird little intricacies of the SDK, your business logic, everything else all tied up in this single code file. You've removed your ability to be flexible. And I actually think this is one of the most important architectural abilities, if you will. Flexibility, evolvability, call it whatever you want. The ability to deal with change is really, really important, particularly with how fast software seems to be moving at the minute. The ability to deal with this can be really helpful. This need to deal with flexibility was actually codified back in the 1960s. With Ashby's law of requisite variety. I only learned about this myself relatively recently, actually. When the variety or complexity of the environment exceeds the capacity of a system, the environment will dominate and ultimately destroy the system. Lots of words, right? Ross Ashby was a cyberneticist and psychologist back in the 60s. And what this in essence means is that if a system can't respond to the complexity that the environment imposes on it, then, well, the environment is always going to win. Always. And I don't know if any of you have read Barry O'Reilly's book, The Architect's Paradox, or his follow-up book, Residuality Theory, is really, really good. If you're into architecture and philosophy and the kind of meshing of the two, it's really, really fantastic. But one of the interesting things that Barry calls out in this book is that software engineering is actually in a really interesting place. Engineering being the important word there. Because if you can compare that to other kinds of engineering, if I was going to design a building, build a building, I'm dealing with a relatively fixed set of constraints, right? The laws of physics don't change all that often. Gravity's pretty consistent. So I've got this finite set of constraints I'm operating within to build my building, to engineer my building. Now, when it comes to software engineering, though, although the software itself is deterministic, right? The reason we write code is because it does the same thing over and over again, hopefully forever. But the environment software operates within is incredibly changing, is incredibly complex. People change. The whims of your CEO deciding that everything needs to be AI now, these are all things that you need to start to deal with. So how can you actually deal with this when it comes to actually writing your application code? And I don't think there's anything new here. It's just practicing good software design principles. Patterns like ports and adapters. Call it ports and adapters, call it clean architecture, call it hexagonal architecture, whatever you want to look at. The fundamental idea of all of these patterns of structuring your code base are separating your application concerns from your infrastructure concerns. With ports and adapters, you've got driving adapters. Driving adapters drive your business logic. This is your HTTP handlers, this is your message handlers. These are things that are going to receive something from the external world and call into your business logic. Your business logic exposes ports. These are the actual business functionality. And your business functionality might need to call out to driven adapters, should I say. This is your database connections. This is your other dependencies that your business logic needs to call. If we apply our Azure functions on top of this, all Azure functions should really be is an adapter. It is adapting that inbound request that comes in from Azure functions and adapting that into something your business logic can understand. You're going to call into your actual business logic. That's then going to call out to whatever your database provider is. Your business logic doesn't need to care exactly what your database provider is. Now, I know what some of you are thinking. This adds an awful lot of ceremony to software development, right? You end up with a project that looks a little bit something like this. And yes, this is actually something I built when I first learned about software design patterns, and it was a horrible code base to work in. You've got interface project, you've got a services project, you've got a repositories project, you've got shared kernel, whatever the heck that is. You've got all these different libraries. You need to make a change, and you find yourself making this change in 10 different code files just to get the thing to work. Don't do this. This can actually be an awful lot simpler. You can break this down into what is in essence 3 projects. This could equally just be 1 project, but I find you can do encapsulation a little bit better if you split this down into 3 projects. I realise there's 4 there, by the way. I'll come back to that in a sec. There's the core project. The core, this is just your core business logic. This is only business logic. There should be no external dependencies here. You should be able to look at this library and understand exactly what this code base does. Here you can see there's something to do with recipes, something to do with handling completed orders. You've got your infrastructure project. This is your actual implementations. This is them driven adapters down at the bottom. This is where you put your code for interacting with your database, your code for interacting with your message broker, whatever that might be. And then you've got your actual application host. This is your driving adapter. The reason there was 4 and not 3 is because there's ASP.NET and there's Azure Functions, 2 separate driving adapters. All these are really in charge of is translating that inbound request and calling into your business logic. And if we actually have a look at that same Azure Functions handler from earlier, but rewritten to practice more of these well-structured code design principles. So now instead of injecting your MongoDB collection, you're injecting your database provider into the actual function handler, you're ejecting your port. Now I realize I've got the word command in there. This isn't anything really related to CQRS. I just like the word command as a piece of terminology. This is a create recipe command handler. You've still got your Azure Functions SDK specific stuff. You would still have your Lambda specific stuff in here because of course this is the job of this piece of code now, is to adapt that inbound event payload into something that your business logic can understand. You've still got your HTTP trigger. You're still parsing the body of the request because that's still something you need to do to adapt that inbound request. And then all you're doing is calling into your business logic. You're calling that port on your business logic, the handle method. If you go and have a look at the handle method, this is just pure business logic. There's no database responsibilities in here. This code could now run anywhere. If we zoom back out, all we're doing is now then returning the result that the function service needs. For Azure Functions, that's just a standard iAction result. For Lambda, you need to return a very specifically structured payload. So what this means now, we come back to the problem we were in. We had an application that was running on Azure Functions, on Lambda, and we now want to run that somewhere else. And practicing good software design like this means that when you need to do that, you need to move your application from one compute provider to another. All you're changing is that adapter in the top left. I'll just do that a few times so you can see that moving. You're changing your instead of adapting an Azure Functions payload, you're now just working with whatever ASP.NET gives you. And if you look at this exact same create recipe endpoint in ASP.NET, now I'm using the more traditional controller style here rather than the minimal APIs just to make this comparison a little bit easier. You see that it is, well, basically the same code as was in the function, right? Because all you're doing is adapting that inbound request, calling into your business logic. You're dealing with the intricacies of this specific framework. If you compare the two side by side, again, you will see that they're pretty much identical, with the main bulk of it is just being calling into that exact same handler. Now this becomes a really interesting conversation when it comes to the idea of vendor lock-in. One of the things you'll often hear if you're going to adopt serverless technologies is that you are now locked into AWS or Azure forevermore and you can never ever get away from working with functions ever again. Whereas a well-structured code base where you're separating the specific concerns of AWS or Azure or Google or whatever it is from your business logic, well-structured code makes this easier, negates some of these problems. And actually, I think it's almost never going to be compute that locks you into a cloud provider. If you're practicing good principles of stateless application design, really it's your data that is going to lock you into a cloud provider. So back when I was working at AWS, I was working with in the consulting part of AWS, and I was working with a big energy company in Europe. And they had a policy that it was Kubernetes everywhere, because Kubernetes meant they were portable. They could move their applications around fantastic. And we were working with them to help them migrate applications from Azure to AWS. For whatever reason they needed to move all their workloads from one cloud provider to another. So we went and spoke to this development team, and they were really excited because they were like, this is going to be easy. We're using Kubernetes, we're using containers, fantastic, this is great. And then they were using Cosmos DB as their database provider on Azure. Now, I don't know if any of you know, but you can't run Cosmos DB on AWS, and Cosmos DB doesn't really directly translate to a service on AWS. So actually, what they thought was really easy, because they'd use Kubernetes, they could run it anywhere, meant that we now had to refactor all their code base and work out how to migrate data from Cosmos to another database provider. Now, that's not to say that you shouldn't use a managed database service, not at all, but just be conscious that it's your data that's going to lock you into a cloud provider, not your compute, at least if you design that compute right. So now you're in a great place, right? You've started off, you've run a really quick MVP with serverless functions, you've shipped that quickly, it kind of works, but it didn't quite have the right requirements. You've refactored that to run on a container now, fantastic, happy days. Helen's back again. She's still not happy, she's slightly happier, but she's, just imagine her slightly less angry than it was last time, but not quite as happy as she looks in this picture, because she's happy that the performance is good. Users are happy that things are responsive. But there's a feature in the front end that you've missed. Users should be able to sort by the most ordered pizza. Now, when this was back in the monolith, whenever an order was completed, the orders module inside the monolith would make a call into the menu module and say, this item has just been ordered. We'll increment a counter in the database. But now you've broken out this microservice, right? Now you've broken out this microservice that's running on a container, and you've got this monolith over here, and there's not really any communication between the two. That's a problem. And this brings us on to what I think are primarily, you can categorize most applications into two different buckets. Synchronous applications or asynchronous applications. Now, I'll define a synchronous application by something where there's a user sat there waiting for a response. A user is blocked, waiting for the call to come back. I use the word user loosely there. That might be a human, that might also be another system. Fundamentally, a synchronous system has someone sat there waiting. How many of you have ever had a user come to you actually and ask you, could you make this service slower and make it break more? That's good, cool. It'd be great if users did say that sometimes, wouldn't it? It'd be nice and happy. Synchronous systems have a very specific set of constraints, don't they? Users want things to be fast, they want things to be reliable, they want things to be performant, they want things to be where exactly you said they were going to be, behind the DNS name, behind the IP address that you said they were going to be. That set of requirements that these synchronous applications have that people are waiting for impose a really specific set of constraints on you. Part of the reason why you chose to use containers instead of functions. But asynchronous applications, and again, I define an asynchronous application by something that's doesn't have someone sat there waiting for a response. Reading a message from a queue, processing a message from an event bus, reading a message from a Kafka topic. These are all asynchronous applications. You don't have anything sat there waiting for a response. And these kind of applications have very, very different sets of constraints, right? Because you've not got a user sat there waiting. In a lot of cases, performance isn't as critical. It's not to say you can't build performant applications with messages, but typically there's not as much of a requirement because you don't have a user sat there. Now, of course, you could take your containerized application you've already got, and ASP.NET gives you with a really nice way to run background services. You can create a class that inherits from background service, and this will allow you to start up a running process on a background thread inside that same running process. Most programming languages allow you to do this in some way. And inside this background service, you can configure your connection to Azure Service Bus in this case. You can start up the Azure Service Bus processor. And then you can handle a message whenever a message is received on the queue. So here you're polling Azure Service Bus. You're processing the message when a message comes in. Now, if you were doing this in the real world, I'd probably recommend using some kind of framework, something like Brighter or Mass Transit. The reason I'm not doing that here is because I just don't want to come across as I'm recommending one messaging framework over another. That's why I'm using the pure Service Bus SDK. Now, if you were doing this again in the real world, probably adopt some kind of messaging framework. Now, when you think about doing this on a container, though, even when there's no messages to be processed, this thing is still eating up resources, right? Because it's sat there, it's still running. Now, you could argue that because you're running this inside the same running process as your web API, well, that's not really a problem because it's resources that are being used anyway. But I think that introduces its own problem. In that, if you get a sudden influx of messages that come in, well, them messages are going to need to eat up resources as they're processed. That's resources that are now no longer available to requests that are coming into your actual API. You know, them actual synchronous requests that need to be fast, need to be reliable, need to be performant. So actually, I'd almost always recommend breaking out some kind of message processor into a separate running process to the thing that's handling your actual HTTP request, just so these two things aren't battling with each other. But when you look at this, actually, we're running this thing on a container now, right? Is this really the pragmatic choice for something that's processing messages asynchronously? Could we not take a walk back up this serverless spectrum and look at functions? Because actually, the core superpower of functions as a service is their reactivity. Their ability to react to things that are happening, to scale up when there's work to do, to scale down when there's no work to be done, do that automatically, and you only pay when messages are actually being processed. And because you've practiced good code design, actually moving that message processor from inside that container to a function is less problematic. So this is an Azure function that's reading messages from Service Bus. You see I've got a Service Bus trigger there as the first argument to that handle new recipe method. I define the queue or the topic that I want to process messages from, and then Azure Service Bus is going to handle the rest. It's going to handle all of that communication. If you compare these two things side by side, you see that they're basically the same. Processing a message with the Azure Service Bus SDK is basically the same code as processing it with Azure Functions. The difference being in that first example, there was all that other code where you had to actually set up the SDK, pass in the connection string, say the message is completed after the fact. Azure Functions handles a lot of that communication for you. Lambda does exactly the same. If you connect Lambda up to an SQS queue, the Lambda service is going to handle all of the communication with SQS, and it's just going to pass the payload of messages to your function. So now we're hitting on what I think is a really powerful pattern for building modern software. Is running your synchronous applications where you've got really specific requirements. Things need to be fast, things need to be performant, things need to be resilient. Use technologies that have been used for ages. ASP.NET, Spring Boot, all these frameworks are really well tested. Run that on a container, expose that to your users through some kind of container orchestrator. And then for all your asynchronous work, all your background work, shift that to functions, using the right tool for the job because, well, functions are going to react to things as they're happening. She's back again. She's actually happy this time though. This is actually how she looks. Because now you've broken out this microservice, you've broken out this menu service, and you're running the web API in a really performant way. It's responding to users' requests, it's nice and lightweight, so you can run it with a reasonably small number of containers, and you've got functions handling the asynchronous processes. And importantly, you've done all of this on your own, and you've actually brought in very little operational overhead here. There's very few other things you need to really worry about apart from your application code itself and dealing with the requirements that that menu service has. Which brings us back to the question that was the title of the talk, serverless or containers. And I hope some of you have probably realized that this is actually the wrong comparison to make. Because serverless is actually just an operational model. It's a way of thinking about running your applications. It's about running your applications in a way that allows you to focus on the complexity your users care about. Containers, simply a packaging mechanism. You can run containers on Azure Functions, you can run containers on Lambda, you can run containers on a container orchestrator. So let's phrase this question a different way. Short-lived or long-lived compute? I think this is a better question. Is the thing I'm building going to benefit from being short-lived, to be ephemeral, to spin up when there's work to do and spin down again when there's no work to do? Or is it better being something that's long-lived, that's sat there waiting to receive requests whenever a request comes in? And to make any of these decisions, of course, you need to understand what it is that your system is doing. You need to understand how users are interacting with your system. You need to understand what the kind of user load is, how these services are actually working, how these services are actually responding. Observability is fundamental to any distributed system. So what I wanted to try to leave you with at the end of this talk is something that you can actually take away. Now, of course, it'd be great working for a pizza restaurant full time, assuming that you get free pizza, of course, but this is actually not that practical for all of you. So I wanted to try and kind of bring together a kind of rough idea of when you might pick one service over the other, or what each service gives you or doesn't give you, should I say. So with functions as a service services, typically you get very little infrastructure flexibility. They're very, very opinionated services. You don't really get that flexibility to say, I need a GPU, I need a CPU, I need a GPU. But they also have typically a max runtime. So Lambda functions can only run for a maximum of 15 minutes. Azure functions are actually unlimited. HTTP functions are 4 minutes, I believe, but generally it's a best practice to avoid long-running functions. These things are supposed to spin up, do some work, be disposed of. If you need more than a long run, you need something that runs for a long time, then containers can be a really good option there. Now, of course, the first thought you might have there is like a batch job, a nightly job that you run that takes an hour. Something you should really think about with that is, can you chunk that batch job up into smaller pieces? Because although you might immediately think, well, it runs for an hour, I need to run it on a container, but if it's actually made up of lots and lots of tasks that all take 11 seconds, well, then running that on a functions where they'll just scale up, all the 11 seconds will run concurrently, and then it'll scale back down again. Payload size is another one. Lambda can only support a max of 6 meg. Azure Functions is 100 meg. Again, this was quite hard to find in the documentation, but it's a default of 100 meg. You can increase that. Again, containers, it's kind of up to you how big you want the payload to be. Now, you might look at them firstly and think, when would I ever choose to use a function? Because there's a whole lot of constraints there that I don't really want to work with. So what are the benefits of actually choosing functions? Well, the first is pay per use. Particularly if you're using flex consumption inside Azure Functions, Lambda has this behavior where you're paying when your code is running, you're paying to the millisecond that your code is actually executing. When your code isn't running, you're not actually paying anything. And also auto-scaling. Now, of course, I realize that you can implement auto-scaling with container orchestrators, with container apps, with Fargate, with Kubernetes. You can auto-scale your applications. Of course you can. Azure Functions, Lambda are going to do that automatically. They're going to do that faster. They're going to do that without you needing to actually define the behavior at all. And finally, the important one is operational overhead. Think about how you can reduce that accidental complexity as much as possible. Whether you're running containers, whether you're running serverless functions, do that in a way that allows you to reduce the operational overhead. So takeaways. Focus on the right kind of complexity. Your users don't care how well you can patch a virtual machine. Your users don't care how well you can upgrade a Kubernetes cluster. Your users care about the thing doing the thing it was supposed to do when it's supposed to do it. They care about it solving the problem you built the service to solve. Secondly, design for flexibility. Think about adopting patterns like ports and adapters or hexagonal architecture. And you don't need to do an awful lot of ceremony to that. You don't need 10 class libraries with each individual layer. You can do that in a really simple way that still keeps that separation between your infrastructure concerns and your application code. And then at a higher level, things like event-driven architecture, where you can build the element of evolvability into your system architecturally. Because you've got events, you can then hook new services into those events. And then finally, choose the right tool for the job. Be pragmatic. If your system would better suit scaling up and scaling down automatically, thermal compute, functions are great. If your system would better suit being long-lived, where you've got a container sat there waiting for requests at all times, do that as well. Now, the last thing I just wanted to talk about quickly is another really quick story. A customer I did some work with when I was at AWS. Now, I can't lay claim for having implemented this solution, but it's a really good example of exactly what I'm talking about. So this company, they had a use case where they needed to process files. Files would be dropped in an S3 bucket, they'd be dropped in a storage location, and they needed to process them. Now, maybe 60-70% of those files were really small, really little, so they could process them in 30 seconds, a minute, really, really quick. And they get a lot of these really, really small files. But then every now and again, they'd get a really, really big file that would take them like 30 minutes, 45 minutes, an hour to process. And because when they wrote the actual code to do this, they practiced really good design of their code. What that actually meant is they could run the exact same container image on Lambda and on Amazon ECS. The exact same container image, and there's ways you can do that. Then they just had a little orchestrator before that. When the file hit the S3 bucket, that raised an event, they started an orchestrator. The orchestrator could work out how long that file was going to take to process based on the size of the file, and they'd route that processing to either Lambda, happens really quickly, done in 30 seconds, happy days, or to a container running on ECS with Fargate when they had these bigger files to process. So it's a really nice example of when you actually think about how you structure your code, how you design your code, where your code can run, you can start to do these really smart things. Now, I'm not recommending you do that for all of your workloads, because adding the code to run a container in both places at the same time does add some extra configuration to your code, but it's a nice example of this idea that actually you can choose the best tool for the job and be flexible between the two. All of the slides, any links, any resources are all on that page on my website. I will be around for the rest of the day. I'm probably going to go and hang around at the particular booth for a little bit. We've probably got time for questions right now, actually. We've got another 7 or so minutes. But after that, if you want to catch me, I'll probably be hanging around there for a bit. And yeah, thank you all very much for coming out to watch me. I appreciate you all very, very much. Thank you.